Welcome to Mr. Frolick's physics classes. In today's lectures, we're going to talk about potential energy, mechanical energy, and conservation of energy. Hello there. In today's lesson, we're going to learn about energy storage and energy conservation. So for now, let's call this here just an idea of energy storage, and we might change this in the future. So let's consider that I have a table and I have a box that I placed on top of this table. Okay? And I'm going to grab this box with my hand and move it back and forth. So in that sense, this whiteboard represents the table and this marker, this eraser, represents the box. So I'm going to put inside on top of like this, and now I'm just going to drag back and forth like this here. So I ask you guys a question. Am I spending energy to drag it back and forth? Yes?
Yes, you spend energy.
Why do you say that?
Well, you are doing work against friction.
Okay. Now, if after I drag it back and forth, I just hold it here in place, and then I release, of course, only the eraser, not the table, just the eraser, what's going to happen?
Nothing.
Exactly. Basically, nothing happens. So what we see is this. The energy that I spent to do work against friction is gone. It's completely lost. It became heat and sound, and I cannot use it. It's just lost. Now let's consider a different situation. Let's say that I'm going to get my eraser and lift this eraser from point A to point B. Okay, so the eraser is just moving up. Am I spending energy to lift the eraser, to do this with it and lift it up? Yes, I am, because I'm doing work against the gravitational force. And you all agree that we are spending energy to lift the box because mainly I'm doing work against the gravitational force. So here is my eraser going up. Now, if I just at this point release the eraser, what is going to happen?
The eraser will fall, with an increasing speed.
Its kinetic energy increases as it falls.
Exactly. The eraser is going to fall in accelerated motion. Okay, so again, I'm spending energy, I'm doing work against the gravitational force, but once I release, this eraser falls, and it falls speeding up. So it's increasing kinetic energy. At the end of the day, what I have in here is this. The energy spent against friction, this energy is gone, lost. But the energy spent against the gravitational pull, this energy can be retrieved. I can get it back.
Retrieved. Can you please explain this better?
Yes, of course I can explain this better. Let's consider this example here. I think is going to make us understand better. So let's say that we have some source of renewable energy. Could it be a solar panel, for example, a wind turbine, or just a tidal system, but something that at some point is going to produce a large amount of energy. And at this point, it's producing more energy than what I need. So the supply is greater than the demand. And I have energy going to waste. What can we do about this? I mean, instead of wasting that energy.
This energy can be stored in batteries.
Yes, that's a possibility. But then batteries themselves will pose a huge problem for us. They open another can of worms in terms of environmental issues. Instead of using batteries, one thing that we can do is this here. We get a low-level reservoir, a high-level reservoir, and we have water down here. And when I get a large amount of energy, this excess energy, what I'm going to do is pump water up the hill. And now I'm going to put the water up here. You see that when I'm pumping this water up the hill, what I'm doing is something equivalent to lifting my eraser. I'm doing work against a gravitational force. I'm spending energy to do that. Now here's the thing. When now my solar system, my wind system, whatever, is not producing enough energy to satisfy the demand of energy, because somehow the demand has increased or supply has decreased, but I need some extra energy. What I can do is let this water come down a system with a turbine, and then I just let this water flow down here. And as this water is flowing down, it's moving the turbine. So a portion at least of that energy that I used in pumping the water uphill is now retrieved when the water is flowing downhill through the turbine, because now this can produce electricity for us. Do you understand now better what I meant by the energy being retrieved?
Yes, now it makes more sense. Thanks, Mr. Frolic.
So, what we can say at the end is that the energy spent doing work against a gravitational force is somehow actually storing, or can be stored, and it can be retrieved. So, this energy storage here, I can relate to the work done by the gravitational force. And the name we give for this energy stored in that sense is potential energy. Okay? So the name we will give to this storage of energy is potential energy. And it's energy that is stored by the gravitational field when you do work against it. In our next step, let's now remember the results of our vertical launch with no air resistance in our free fall studies. So, we studied before that I launched my object, in our example that we studied before, with an initial velocity of 30 meters per second. And then, 1 second later, this object had reached a height of 25 meters. And 2 seconds later, it had reached a height of 40 meters. 3 seconds later, it was at 45 meters at the highest point. Remember that the object is going to go up and down on the very same vertical line. I'm representing this sideways, so the picture is not superimposed. With 4 seconds of motion, it was coming down with negative 10 meters per second of velocity, and it was at a height of 40 meters. Then, 5 seconds, it's going to be coming down at 25, it's going to be at 25 meters with a velocity of negative 20 meters per second. And at 6 seconds, it's going to be reaching the same launching level with a velocity of negative 30 meters per second. So this is what we discussed before when we talk about free fall and vertical launch. And you see that we have a symmetry. The time going up equals the time coming down. The velocity at every point going up is equal and opposite the velocity of every point coming down, or the speed going up equals the speed coming down. The reason for this symmetry is this here. When my object is going up, velocity is up, the gravitational force is down. So it's opposing the motion of the object, slowing it down. And when the object is coming down, velocity is down, gravitational force is still down. It's now in the same direction of motion, and it is speeding it up. Let's change the focus of our conversation a little bit this way. When the object is going up, the gravitational force is doing work against the motion of this object. It's doing negative work, and it is taking energy away from it. Now, when this object is coming down, the gravitational force is doing work in the direction of motion. So it's doing positive work. It is actually giving back that energy that the object is receiving. Notice more, that the object has, at every single same level point, the very same amount of kinetic energy it had going up. So the kinetic energy coming down equals the kinetic energy going up, which means that the amount of energy that the gravitational force takes away when it goes up is exactly the same that it gives back when it comes down. If we now think about, put together the idea of the storage of energy that we discussed a while back on the side of the board, what people start believing or reasoning was not that the gravitational force is taking energy away and coming back, but it is storing in a form that we just called potential energy when it's going up, and then it transfers that potential energy back to kinetic energy when it's coming down. So what people thought was that there should be some kinetic energy form. We have already seen that that kinetic energy is 1/2 of mv squared. Okay? And that there should be some potential energy form. And that potential energy form, we are not really so sure exactly how to calculate, but I do know that somehow there should also be a total mechanical energy, and that in a system like this one, the total mechanical energy should somehow be constant. So this was roughly the idea. What I'm going to do here is just a generic study. So I'm going to grab any point, consider any point, for example, this point to be my initial point, and maybe this point to be my final point. Notice A and B are just two generic points of my study. And I'm going to consider the work done by the net force to go from A to B. We've seen before that this equals the change in kinetic energy, which is going to be the kinetic energy of B minus kinetic energy of A. Now, the only force doing work on this system is the gravitational force. So the net force is actually going to be the gravitational force. And we saw in class that the work done by the gravitational force equals negative change in, negative mg delta h. Or that the work done by the gravitational force is going to be negative mg h of b minus h of a. If now I get this result and put back in here, I'm going to have that negative mg h of b, negative with negative becomes plus mg h of a equals kinetic energy B minus kinetic energy A. Or, if now I rearrange and I put everything about B on the right-hand side and everything about A on the other side, I'm going to have this here. mgh of A. I had a negative kinetic energy of A, becomes plus kinetic energy A, equals to negative mgh of B goes to the right-hand side, plus mgh B, plus kinetic energy B. Now, let's see what we have in here. I want to move into this orange box. I'm sorry I'm a little bit disorganized, but the board is relatively small. We'll talk about some form of potential energy that is related to the gravitational force, the work done by the gravitational force, that combines with the kinetic energy, giving us a total energy, and that total energy should somehow remain constant. Well, now let's see what we have. Kinetic energy combined with mgh, which is a term that came from the work done by gravity, and mgh plus kinetic energy at point A, which is my initial point, equals to mgh plus kinetic energy at point B, which is my final point. But A and B are any generic points I chose, arbitrary points, which really means that for any 2 points I consider, this combination will remain the same, will be constant. So we're going to define here now, we will define potential energy gravitational as mgh. We'll also define mechanical energy. Instead of total, let me just write this as mechanical energy, my bad, as being the potential energy plus the kinetic energy. And if it is a system like this one, where only the gravitational force or a force similar to that is doing work, this combination will remain constant. So let's just repeat. We just define potential energy, that energy that is stored by the action of the gravitational field, as being mgh. We also defined the mechanical energy as being a combination of potential energy plus kinetic energy, and that this combination in this kind of system will remain constant. In order for us to better understand this concept, we are now going to analyze the PHET simulation energy skate park. So I'm going to have here the ground level, and then I am designing a track that is roughly like this here. And then we place a skater at this point, and this skater is going to go down, move on the bottom, and then come back up. At first, there is no friction on my system. And what you guys can see is that while the skater is coming down, when he's moving down, his kinetic energy is increasing, and the potential energy is decreasing. But notice that the combination of the two remains the same. When he's running through the bottom, the kinetic energy and potential energy roughly don't change. But now, when he goes up, I'm going to represent this here inside because I'm too close to the board, his kinetic energy will go down, but the potential energy now is going up. But again, as they are going up and down, the total energy remains the same. Please see him going back and forth a couple more times. I'm switching now to the pie chart instead of the bar chart. So the pie chart gives us an idea about 100% and how that moves back and forth, a different visualization. Okay, let's now stop here. And now let's add friction. So what I'm going to do now is add friction. And when I add friction, you'll see now that my skater will start at this point, but it does not really reach the very same level as before. The maximum height is slightly less, and then slightly less, and slightly less, and so on. What happens is that as I'm changing from potential energy to kinetic energy, thermal energy is going up. Heat. This is energy that is becoming a generic disorganized vibration of molecules and spreading to the neighborhood, and therefore no longer being able to be used by my system. And even when it's going up here and I'm changing back kinetic to potential energy, this thermal energy is going up again. And again, and again, and again. Until actually my skater kind of stops at the bottom with no more energy to go up or to move anywhere, and all of the initial mechanical energy we had became thermal energy. Let's try to understand this going back to the force diagram system here. So when I toss my object up, for example, 30 meters per second, then goes down to 20 meters per second, it's going to reach this 20 meters per second at a height that is less than 25, perhaps 22, and less than 1 second. It goes up. On the way down, it's not going to move as fast. Its speed is going to be perhaps 15 meters per second. And then when it reaches the lowest level, maybe the final velocity, the final speed is going to be 20 meters per second, or the velocity negative 20. The reason is this here. This is what we had before. Object going up, gravitational force is against the motion, is taking kinetic energy away from it and storing. Object coming down, gravitational force is now in the direction of motion, is taking potential energy, pushing back into kinetic energy. The thing is that if now I add air resistance, when the object is going up, air resistance is down. So from a force perspective, the object slows down faster than before. Okay, the object slows down on the way up faster than before, because now I have more force slowing down. From an energy perspective, it loses more energy than before because I have an extra force doing work to make it slow down. But when the object is coming down, air resistance will now change. If you remember, this kind of force depends on the actual distance traveled. It changes with the direction you're moving. So from a force perspective, it's not accelerating as much as before because now I have a force that opposes the gravitational force. From an energy perspective, the energy does not come back as much as it was lost because I have a force doing negative work on the system. So I still have a force that is getting kinetic energy and changing into something else. And that's how that energy then is being lost. Okay? I hope that this example has been useful, that you have understood all of the simulations and the videos, and what we should do now is work a couple problems to see how this actually fits in. See you around.